Welcome back, everybody. It's good to see you all again, and we move on from the beginning uh, vegetables and milk to maybe a little bit of meat, but hopefully it won't be too hard for us. I'm going to share the screen to get us started. All right, share. Here we go. So here we have a nice picture of an astronomer around 1513, and he's using an armillary sphere to divide up the heavens, and we see the sun and the moon as part of the objects of his observation. As a reminder, I'm Honorable Lord Taran Saraev. I'm a Mongol of the 13th, 14th century, the height of the empire, especially the Golden Horde. My areas of concentration that I love are pre-17th century astronomy, pre-17th century alchemy, Mongol persona, and heraldry. And my email and website information is here for those of you who may be interested in that. There's certainly a lot of bibliography and further resource information on my website. I think all of you were here before, but just as a reminder, the kind of tradition that we're talking about in all this is the Ptolemaic tradition of astronomy, which started out in Mesopotamia and was developed and solidified in ancient Greece, and went over into the medieval Islamic and Arabic world, where it was advanced and brought back to Europe and the Crusades, and further developed into the Renaissance. And this is all one string of astronomical learning, and it's generally called the Ptolemaic tradition. It's called that because of Claudius Ptolemy, who wrote this work called the Alchemist, which is kind of an Arabic word that means like masterwork. And his original title in Greek was something like 13 books on the motions of the heavens by Claudius Ptolemy, or something of this nature. It's the culmination of Greek astronomy, and was considered to be what you needed to do to be a serious astronomer from, the time of its written in the BCE era to all the way in the 1600s. Even Nicholas Copernicus, who wrote The Revolution of the Heavenly Spheres, which switched us from the Earth-centered view to the sun-centered view of the world, was a dedicated student of Ptolemy. And his work is kind of like a rewriting of Alchemist for a sun-centered universe as opposed to a Earth-centered universe. And so he could be considered the last great astronomer in the Ptolemaic tradition. But thinking about the world that way, here we have an armillary sphere. We see the Earth in the center. This band here with the zodiac signs on it is called the ecliptic. It's the path of the sun. The middle bar here is the equator, and then above it and below it you have the tropics, and then below that you have the Arctic circles. You have the prime meridian running this way, and the point directly above the Earth and below the Earth are also represented here. Sometimes you see it with a horizon. Now, the sun and the moon and the planets all travel across this path called the ecliptic. Of course, we know now that the ecliptic is really the path of the Earth, not the path of the sun, but it's still the way they thought about it, so we need to think about it in that fashion. If we were to look at it flat, you might think about this picture here. In the center, you see the Earth, and then you have the elements all around the Earth, and then you have a circle of the moon's orbit, Mercury's orbit, Venus's orbit, the sun's orbit, Mars' orbit, Jupiter's orbit, last Saturn's orbit, and then you have the sphere of fixed stars, and then you just have some math things there to help divide up the heavens for us. And so another way to look at the heavens. Let me stop my share real quick, and I'm going to return us to look at the celestial globe I have here. Once again, we see the same kind of like surveyor's perspective of the universe, where you have the Earth in the center. The ecliptic is the path of the sun as it orbits around it, and the constellations of the zodiac are at different parts of it. When the sun is in its path in one of the constellations, for example, in this case, let's see here, Aquila, then when the sun is in December, it's in Sagittarius, and so the constellation, the sun's path meets with the constellation Sagittarius, so you can't see the constellation Sagittarius where the sun is said to be in Sagittarius, and that kind of shows us where the sun is on its path. And so Then you have the background of fixed stars represented as this plastic globe. Once again, the equator line with the stick plastic line, the ecliptic runs the path of the sun. We can see the yellow ball moving around inside, and the fixed background of stars. Now the moon and the planet's motions would all be inside that plastic globe. All right, let's move back to our PowerPoint. So probably two of the more important things to understand is solstices and equinox. So here we have a position with the Earth in the center. We have the summer solstice here, the winter solstice here, and the equinoxes along the line. And we can see everything kind of adding up very nicely. Let's see here. So let's start talking about the equinox. Equinox is commonly regarded as the instant in time when the plane of the Earth's equator passes through the center of sun. The words equinox come from Latin words meaning equal and nox meaning night. So during the equinox, there's equal hours of daylight and sunlight. In the northern hemisphere, the equinox that occurs in the spring is called the vernal equinox, or the spring equinox, and the equinox that occurs in the fall is called the autumnal equinox, or the fall equinox. Now here, you have the Earth's plane of the equator. Now when we're talking about the plane, the big circles on the celestial sphere are imagined to go out into the galaxy. So you can imagine like a big armillary sphere over the planet Earth, and this helps us divide up how we go. So this would be the plane of the Earth's equator. Here's the ecliptic, the annual path of the sun. And so when the sun's position on the ecliptic matches where it is on the plane of the equator, that is when we have our equinoxes, when we have the same amount of daylight as we have nighttime. So let's go back to the next slide. Now, the dates previously, the dates of equinoxes changed somewhat because of how we know because of the Earth's the sun's passage around the Earth, or the Earth's passage around the sun, as we think these days. And so there's these cycles of leap years, which are around 400 times, and none of these dates are set. But the 21st of March is roughly the vernal equinox. The 21st of September is roughly the autumn equinox, and there's 2 or 3 days that you might can imagine in both directions. Gonna pause here to see if there is any questions. I'm looking in the chat to see if anyone has any questions, and are we all good? All right, moving on. So, solstices. A solstice is an event that occurs when the sun appears to reach the northernmost excursion from the celestial equator and the southernmost excursion of the equator. Of course, we get the most light in the summer and the less light in the winter. The word sol is Latin for sun, and sister kind of roughly means to stand still. So when the solstices, the sun kind of appears to stand still from its daily path around the Earth, or vice versa in this case. Now let's go 2 things back to look at our map again. And so here we see this is the northernmost point. The sun goes from its equatorial plane, and the winter solstice is the southernmost point. It goes from its equatorial plane. So here's that picture again. And so this is kind of solstices for us. It's important, and these are important to take note of. The sun is probably the most important thing to learn when you're starting astronomy, is how to predict the sun and how do we know the things about the sun, because this works into how we relate the calendars, and so it's important for us to know the sun in order for us to move on to the other objects. We're thinking about methods of observing the sun and how we learn things. We might think first about the gnomon. The gnomon is basically a vertical pole or stick on the Earth, and local noon is the time when its shadow is the shortest. If you are taking shadow plots every day, The summer solstice will be the shortest noontime shadow plot out of the year, and the winter solstice will be the longest noontime shadow plot out of the year. Now, as a reminder, what we're talking about here when we talk about these shadow plots is the sun creates a shadow on the ground. The gnomon creates the shadow, and you plot where the end of the shadow is. And it will create roughly some sort of a curve throughout the year. The shortest plot of the day is always true noon, and that points north where we are here in North America. And most in the northern hemisphere, I believe. Now, you can take this plot every day, and where true north is every day, and true noon will be the shortest plot, but each day that shadow location will move according to the sun's timing. And so the longest noontime shadow will be for the winter solstice, and the shortest noontime shadow will be for the summer solstice. Now, there are some limitations to using the gnomons to determine when the solstices are. And these are, the solstice is not always occurring at noon. Sometimes it occurs between noontime measurements, and sometimes there is a fuzziness relating to the shadows. So when you're trying to look at these shadows, sometimes you're not really sure where the shadow ends and where the shadow doesn't end. This can create some error in your calculations. But so that's a limitation. The other limitation is sometimes the hour of solstice could occur in the middle of the night, for example. And so you wouldn't be able to judge by a noontime shadow plot. And it could occur at other times. So in those kind of situations, you have to be taking shadow plots every day, and you would know the solstice has occurred when you were in between the two shortest. And so it's a good illustration for us. There's another method of determining this, and you could call this the meridian quadrant. This object is described in the Alchemist. A quadrant is a fourth of a circle, as we talked about before. Meridian quadrants are not things that you would hold. They are big things. The one in Alchemist is guessed to be around 18 to 36 inches, and it would be a stationary block. Maybe it would be painted on a wall. You would have two pins, kind of like a gnomons, except for instead of vertically, they're horizontal. The top pin and the bottom pin are used to determine plumb, to make sure that the device is level, as well as the top pin or peg is used to determine the shadow line for the degrees. So you have divided the quadrant into degrees, half of a protractor, 1/4 of a circle, and you align this with the meridian zenith. So your local meridian is wherever the north-south line, and so you would align the meridian quadrant on the meridian level, and then the sun's shadow would cast the peg for the degrees that the sun is. And of course, you can. This is much more precise than the gnomon because there's less fuzziness attached to shadows. It's more reliable for determining equinoxes than it is solstices because of the mean of several noontime altitude measures for the solstice is not always at noon. And usually the solstice is like, you can, with this method, get the solstice to the nearest half day. So this is an object you can use to tell those things, and that's roughly how it works. Here's a fun method. It's an equatorial ring, and it's an object described in The Alchemist, and the large metal ring is placed in the plane of the equator, which is a certain offset from wherever you are, and you can usually be able to tell it by looking at a celestial sphere or an armillary sphere. And spring and summer shine on the top. The sun shines on the top and never the bottom. In fall and winter, the sun shines all day on the bottom face. At an equinox, the shadow on the top part will fall on the lower part and be a thin ring in the center with equal strips below and below. So if this ring is tilted at exactly the equatorial plane on the equinox, and only on the equinox, the sun will shine, the top shadow will shine directly on the bottom ring, and so you'll be able to know the exact equinox. A big weakness in this is it's very difficult to keep this ring aligned to the plane in the equator. And if you don't have it aligns to the plane and the equator. It produces a lot of false readings. So that is a big problem with that. Let me see here. Going to try to pull up my chat again so I can see how we're doing talking about these kind of tools and methods. I'm reading the chat to see if anyone's saying anything. It appears we're all still quiet, so I'm going to assume it's safe to move on. Closing the chat. Now, we start talking about the lengths of the year. From about the 3rd century BCE, we knew that the year was 365 and a half days. Different calendars work this out in different ways. It's important to know that there's something called a tropical year, and the tropical year is a little shorter than 365 and a fourth days. A tropical year is the length of time it takes the sun to travel from one point on the tropic to another point on the tropic. Remember, the tropic is one of those rings in the celestial sphere and our military sphere that go around, that are imagined to go around the outside of the universe. Now, suspicions were very early that the length of the year was variable because of this kind of thing. But these suspicions ended with more observation, because observation seemed to indicate that it wasn't variable and the model was about right. Seasonal days, however, are not always constant and equal, so you don't always have constant and equal seasons. So not always is, spring, summer, winter, and fall have exactly whatever a fourth of 365 and a fourth is. There's always some variation. And these things have changed over time. The longest season in the medieval era was the spring, and nowadays the longest season with the most days is the summer. All this, of course, all this spread of variation is called the solar anomaly or the solar inequality. Now, if you want to predict where the sun is at all times, you need to develop a solar theory. And from the ancient Greeks, we knew that there were about 4 parameters elements we needed to make an accurate solar theory. We need to know the typical length of the tropical year, which determines the rate of the sun's motion of the circle. And again, the tropical year is the length of time it takes for the sun to go from one point on the tropic to the exact same point on the tropic. And that's a little shorter than the 365 day and a fourth. But the precise measurement makes your solar theory better. The longest apogee, which is the longest point it is from the Earth, this angle specifies the direction of which the center of the eccentric is located as seen from Earth. You also need to know the eccentricity of the eccentric circle. Now, a eccentric circle is a circle with an offset center, roughly. And the ratio of the Earth center of this eccentric to the radius of the circle. These quantities specify the amount of the center of the eccentric, how much it's displaced from Earth, to figure out exactly how you need to do it. Now, the eccentricity sometimes was perceived to be 0, and that's where they started, and then they moved out from there to try to get their model more accurate. And then there is the longitude of the sun at one particular moment. If you have all of these things, you should be able to, if you have them accurately, you should be able to accurately predict where the sun is at any given moment, and you should be able to get the solstices and equinoxes as well. 2 different models, very different models, were based to solve this. One of them is Hipparchus's eccentric circle model, and the other one is the concentric differential model that was devised by Ptolemy. Now, I do want to stop and check the chat real quick because I mentioned a lot of technical things. Maybe I glazed over them too quickly, so I'm looking at the chat again to see if there's any questions. Still silent, so going to plan on moving on. Closing the chat here. All right. Next, we have Hipparchus's eccentric circle model. And this was the accepted model virtually by every astronomer until the 16th century. Ptolemy's displaced it. But whether you use this model or whether you use Ptolemy's model, the mathematics is the same. This model was taken to be the case at first, because it had less changes to the overall model of the universe. Ptolemy's had a little bit more, and so it wasn't seen to be as good until Ptolemy gave his reasons for it. In this model, the Earth is at the center of the universe, of the sun's orbit. But the equinoxes are still equally placed. So here you have the Earth at the center, you have the autumnal equinox and the vernal equinox, summer solstice and the winter solstice. And so this explains the seasons equally, why that you get those and why these are different. And the sun appears to be moving very quickly around the Earth at apogee, at its very furthest point, and very slowly at apogee. Excuse me, I have it backwards. Perigee is when the sun is closest to the Earth. Apogee is when it's furthest away. So at apogee, the sun appears to move much more slower. At perigee, the sun is perceived to be much more quickly. And this is because of distance. And they explain this very well in geometry. And so this model explains how everything could work mathematically and gives you accurate predictions. The other model that does that is the concentric, different, and epicycle model. This model is a mathematical equivalent to the eccentric circle model. So mathematical equivalence means they produce the same results. You get at them at different ways, but the end prediction would be the same. Now, this allows the Earth to be, the Earth is not quite at the center here. It's at a deferent. Well, actually, this does allow the Earth to be there, I'm sorry. And here you have, and then here you have the planet, or here you have the sun, and the sun is not necessarily going around a straight line. It's running around an epicycle around this point. This point, K, represents the solar anomaly in the center of the thing. The deferent is the line of the sun's path. This path is still how it goes along these angles. So the sun appears to be going around this circle while some invisible point is holding it around the deferent. And this is the solar anomaly model known by calculus in the 4th century, and it's known to be the equivalent of the two models. Now I'm mixing up my planetary theory and my solar theory. So this is not really the solar theory that we went with. The solar theory that the Greeks went with was the one I was talking earlier about Hipparchus' eccentric models. And you see I have that written here in the text. But the only reason this model was favored over the other model particularly was the Earth is still at the center. And that moves a little bit with planetary theory, but that's a different reason for the movement. And so with the solar theory, we're still mostly sticking with this model. But both models produce us, the same results. I'm going to check the chat again just because I was a little crazy there. All right. I would ragin, anyone still attending at this point, is science learning. We're totally all digging this. Oh, excellent. Well, I hope you guys all are digging this because it's fairly mathematical. Well, I'm still being light on the math, but it's fairly heavy science-based. Yeah, the casual people are probably not here at this point in time. Let's go to the next slide. We're here now talking about our moon. We are looking at the lunar phases. Here you have the Earth in the center, and you have sunlight. And we notice that the Earth is here, and the moon is here, and the sunlight is going this way. But if you notice, this light that is reflecting off the moons is coming from the sun. It's not coming from the Earth. A lot of people think sometimes when you see the crescent moon that this is caused by the shadow of the Earth. Well, this is only the case during a lunar eclipse. The rest of the time, the shape that we get from the moon is based on the angle of the sunlight hitting the moon, because the sunlight is known from the moon. And this was known by the ancient Greeks, and this was for the most part an established fact from the time period of the ancient Greeks onwards. So this is not something that people thought they were seeing the Earth here. Although this alarming amount of people today think the moon's light is caused from the interference of the Earth, but that is not the case. Two influential people to talk about Anaxagoras, I know I'm butchering this name, in Athens in 480. He was saying that the moon gets its light from the sun, and ellipses are interpositions of the Earth, sun, and moon. Now, he believed the heavens were physical matter like the Earth. The moon had moons, valleys, and ravines just like the Earth had, although he was one of the people who believed in a flat Earth, and possibly other celestial bodies beside the moon. But by the time we get to Aristotle, we're back to the spherical Earth, and pretty much everyone accepts the Earth as a sphere by Aristotle. And he clearly states that the Earth is a sphere, and the spherical shape results of natural tendencies of things to move towards the center of the universe. So he approaches the shape of the Earth through philosophy more than physics, but it lies the way it is because of how the bodies are composed. This explains the shape and immobility of the Earth, because remember at this time they believed that the Earth was rest at the center of the galaxy. These are Aristotle's presuppositions. And remember that not all Greeks held to Aristotle's presuppositions. That was just where you started learning, was with Aristotle's presuppositions, and you moved on and tried to explain how you thought it was through your mathematics. The 4th century, it was settled that the Earth was a sphere. Ptolemy, Theon of Smyrna, and Cleomenes all supported Aristotle's positions that the Earth was neither flat nor hollow, and many arguments were made to prove the sphericity of the Earth, such as the delay of dawn regionally, local times of eclipses, arguments from sailing ships, and arguments in irregularity in mountains and valleys. So these were some of the arguments that they proved to point at this point in time. Now, let's see here. Aristarchus of Samos in the 3rd century BC worked out roughly the size of the Earth and the size of the planets and the moon compared to the Earth. Now, he was accurate within his measurements, but he was not accurate to what our measurements are today, because his observations had errors in them, and so those errors replicated themselves in the mathematics. But his method of estimating these sizes was considered to be correct. He worked, and so the moon and the sun were known to be about the same angular apparent size. They know this from eclipses because the moon can block out the sun during a solar eclipse, and so it's about the same angular size. Annular eclipses were not as observed as apparently, and so that could also be described in more detail as you were looking more closely at those things with authors who dealt with those issues. But for the most part, as we're looking at annular eclipses, or when the moon does not completely cover the sun, but there's a ring of light around the sun, like we're having tomorrow, those kind of eclipses were not dealt with as much and are kind of outside of the scope of what we're talking about now. And with the lunar eclipse, the Earth comes between the sun and the moon, but only during full moons. So you only get solar eclipses during new moons, and you only get lunar eclipses near and full moons. Now, there are 2 charts here that we should both pay attention to. The first one is the lunar eclipse here. We have the sun in the background and the Earth. And the Earth shadow is able to block out the light on the moon. And this is when the eclipse happens in full umbra. Now up here we have the solar eclipse, and it works just differently. The sun's light is here, and the moon's light is here, and this shows how the Earth's shadow is in the full shadow of the moon, even though this preserves the sizes of the sun, the moon, and the Earth. And as I said, his distances were very close. Okay, got to check the chat one more time. If we can. All right. Nothing in the chat. Going to assume we can keep on going here. So if you're interested in how he worked out those things, Aristarchus of Samos. Now, months and the full moon cycle. Here, we understand that there is a lunar phenomenon, much like there is a solar phenomenon. So the typical month, our tropical month, is defined as the moon going from one place on the tropic to the next point, or 1 point on the ecliptic to the next point on the ecliptic, and this is roughly 27.32 and some change days. A synodal month is divided differently. It's between full moons, how long it takes to get full moons. And it's about 29.5306 days. And this is because the sun's advancement on the ecliptic, and so the moon must travel a bit further than 360 degrees to make all these kind of things work out. Now, the moon moves at variable speeds, faster at perigee and slower at epigee. And the way they worked out the moon cycle is to complete one cycle of all of the different stations of the moon would take around 18 to 19 years. You know, there's all those talks about the ancient Druids. They said it took 19 years to make a Druid, and a lot of people thought that was because that's how long it would take to see a complete cycle of the cosmos. Because the moon cycle, I think, is one of the ones they say is one of the long ones. Here we have a picture as well from a medieval 14th century illumination that shows the light of the sun illuminating the moon at different points in time, and that light not coming from the sun and not coming from the earth not interfering in the moon's cycles. And so we see once again this kind of situation. Now this is kind of where we come to the end of the material. I do kind of want to say a little bit more. Let me end this share. Now the lunar cycle I went with the least because it gets much more complicated. In the next class, we're going to try to look over the different kinds of planetary motion, and so see how that completes to the lunar and solar motion. I was able to go through that information pretty quickly, and so is there anyone who would like to ask any questions or have any comments, things that might add or? Very glad all of you have stuck in around. This is a very, I guess, a different kind of material than we ordinarily would have, and it's somewhat a little bit more theoretic. But it was seen that what we looked at in the first class was the summary of what different kinds of things could be done with astronomy. The second class, we learned about how using different kinds of tools to start plotting the things that are going on in the heavens and knowing when they are. In this class, we started looking at the important values of different phenomena with the sun and different phenomena with the moon to kind of start working on our calendar. Solstices and equinoxes are where we usually draw the line for our seasons, and how we reach this annual solar cycle is how we determine our years. And for the most part, calendars are solar. The Chinese calendar is a lunar calendar, so you would have probably again this 18, 19-year cycle. But when you're working with a solar calendar, the offset of days between the tropical year and the other in the 365 and a fourth year can make a huge difference as far as your predictions. Questions, comments, snide remarks? I know I'm sounding like a broken record here, but I really want to keep pointing people back to Evans' The History and Practice of Ancient Astronomy and Ptolemy's Alchemist. Because with these two things, you basically get the theoretical framework you need to do the astronomy. And it's much more fun to be out taking the solar plots and seeing if you can make an equatorial ring work, and making your own meridian quadrant so that you can accurately tell the details than it is necessary going through all these things. And Evans' book as a pre-alchemist really pushes you to go out there and make these measurements for yourself and see how these measurements work out when you do them. Because while it's all well and good to talk about these, when you actually go out and make shadow plots and are dealing with the fuzziness of your gnomon, and when you're actually trying to tell solstices and equinox from quadrants and rings, you really appreciate how the Greeks set up all this further. All right. Well, that's it. I guess we can end the recording portion of it and allow people to talk who don't want to be on the recording. And as before, I will hang around to talk about astronomy with anyone who would like to until 3 o'clock, when we will start our discussion on planetary theory.